plus additions from the flux burning. So the flux has two purposes. One is that it makes the metal of the rod into weld metal, which is having the property that we are talking about. When you say I have got 70,000 tensile strength, it is of this, not of this. This has melted and gone. So no question where it have any property. In addition, shielding atmosphere, basically carbon dioxide shield is created to prevent excessive oxidation. Carbon dioxide itself is oxidizing, but it's controlled because we know it's there, so we can take care in the covering. Slag layer is formed to protect the weld metal, hot weld metal from further oxidation. And like that, we proceed getting into the, this is your depth of penetration because we have some amount it will go in. We don't really care how much it goes in because we want surface melting. Once the surface is melted, it will join. But this is a consequence. We cannot stop at the surface, so it will go some depth below, and then you will have something called dilution. That means this metal's chemistry will mix with this chemistry and make net chemistry, which is something which can be calculated, of course. Those things are important in stainless steel typically to get the proper microstructures. So this is the schematic of the system where you have got this power source, which may be AC or DC with its controls. That means basically we are setting a value of current. In SMA welding, we don't set voltage, we set current. So once the current is set based upon the electrode size. So if I have a 3 mm electrode, manufacturer will tell you on his box, use 90 to 140 ampere. You're not supposed to use more. If you use less, it will not be stable. If you use more, you lose pattern. So you know when I'm getting excess pattern, what that guy has done. So you have the electrode, you have the arc, you have the weld metal moving, and this is a manual process. And you get your reasonably very good clear weld metal. If you tell the welder that there is X-ray on the job, he'll give you good job. If you tell him no X-ray, he'll give you rubbish. So you have to not let him know that I'm not doing X-ray or anything like that. Okay, now we have to understand welding core wire. What is the chemistry? Okay, this is our core wire. Core wire is this fellow, core wire. I said it's metal. What metal? I'm going to weld 516 grade 70. I'm going to weld 516 or whatever. Low alloy steel, high alloy steel, whatever it is. Will my core wire change every time? Yes. So when I'm welding carbon steel, what I'll do? I'll put carbon steel wire. And when I'm welding low alloy steel, low steel wire. That means every grade I must have a different wire available. Yes. No, not necessarily. Some range is permitted. Yeah. So because this is because I have got this flux coating here, I can put alloying elements from the flux. So the core wire is basically a mild steel wire. It's good for making the arc and good for depositing iron. Now to make it alloy to match with the base metal, that is all coming from the flux covering. Now it cannot take full range. So even though theoretically I can have this carbon steel wire and make a stainless steel deposit, but it's not very popular. So like if I need stainless steel deposit, I have got 304 stainless steel and 361 stainless steel and so many. So I don't have to have a grade for each. I can put a 304 wire and make 316 weld metal. Doesn't have to be for every grade I need a separate wire. That depends on the manufacturer's discretion. So this core wire, which is for the carbon steel I'm talking about, this is the standard IS 2879, and it gives you a chemistry, carbon, manganese, sulfur, phosphorus, copper, 1,5. These are all maximum percentages. Basically, it is a dead mild steel iron wire giving you iron, not weld metal. Weld metal is coming from the covering, alloying of the covering. And now we want to talk about what is the electrode designation, because when I got 51670, I want a 70,000 tensile strength. When I have 51660, I need a 60,000. I don't want to overmatch because I get no credit for it. If I'm welding to 51670 to 60, I need only a 60 weld metal. That is what the code says. The lower of the two must be met. By making it stronger, I can put 80,000 weld metal also. I get no benefit from it. So it's going to cost me money. Why should I do that? So then we go for the electrode designation, where you see that this E stands for electrode. Then these two XX, they stand for the tensile strength in KSI. So E70 means 70,000 is the UTS of the. If you take a all well tensile specimen, you will get a yield. But if we are doing a procedure test where we are taking transverse specimen, there is no question of yield. Whose yield are you checking? You have got a weld metal, base metal, heat affected zone. Whose yield? You don't know. So we talk only tensile when we are talking of transverse tensile test. Obviously, when I got a 51670 plate, I need to have a matching electrode of that matching strength. Then I will see other things like my impact. My 70 is good up to -29, but I need -46. So I'll say that to look for some other electrode, I will go for 7018-1, which will give me 18 C1, C2, C3, anything. That's up to me. So you got 70 here. Then you have got the next YY digit, welding position in which electrodes are suitable, type of covering, and the kind of welding current for which the electrodes. See table 1. So it will describe if I have got 15, 16, or 18. The 1 designates all positions, and 5, 6, and 8 are low hydrogen. What is low hydrogen?
Five ml per 100 grams.
What?
5 ml per 100 grams.
What is low hydrogen? I didn't ask how much is low hydrogen. What is low hydrogen? And anyway, for your correct definition, a hydrogen controlled electrode is one which will deposit not more than 15 ml of hydrogen per 100 gram of deposit. Okay, so normally it comes below 15, it is hydrogen controlled. Then there are stages 0 to 5, 5 to 10, 10 to 50. So depending on what you want, you can ask for that much of this one. So now where did the hydrogen come from?
Moisture. From here,
Also,
it's come on the this flux code.
so I have got moisture, air. That's flux coating.
Yeah, let's be clear.
And one more
Base metal.
base metal. Can't see hydrogen base metal.
Moisture.
It's moisture. Air moisture. The metal does not absorb moisture. No? If it's wet, obviously you will try it. It is from simple words. Rust is not iron oxide, remember. Rust is FeOH3, hydrated iron oxide. So the H is there. There is rust, you will say FeO, iron oxide. No, then it won't matter anything. But because the OH is there, that breaks and the H is released and goes into the weld metal. The H I told you is released because the temperature of the arc is too high, 6,000, 5,000, whatever you want to say. So H2O, which is coming from any of these, is breaking up. The O gets taken care by the flux and slags. Oxides can be removed. The H goes in the weld metal. And the solubility of H, iron, mind you, not H plus, is very high in molten weld metal. The moment the metal solidifies, the solubility goes down. Now the hydrogen has to get out because it is super saturated now in hydrogen. And so it doesn't know that this is the top, or this is the bottom, or this is that away. It keeps moving around somewhere. Somewhere two hydrogen atoms may meet and they form a hydrogen molecule. Then that fellow can't move anywhere because the volume has gone up. The mobility is gone. So if too many hydrogen atoms meet inside the metal and make the molecule, there will be total deformation at that point because volume has gone up, and you may get embrittlement and cracking when the matter is excess. Otherwise, most of it goes out. And if you heat this sample at 250 before you allow it to cool, then hydrogen coming out will not cause cracking. So if you have a real problem with hydrogen, immediately after welding, don't allow it to cool. Just let it go to 250, heat it, and keep it for 10 hours. All the hydrogen will come out, or 16 hours, or whatever. Okay. So now you have got the E7018. The difference between 5, 6, and 8 is about both all are low hydrogen. But this, if you read the tables, this has got iron powder addition, and 5 and 6 don't have iron powder addition. And all those details you will get over there when you see the tables, what is showing over here. Then additional supplemental designators, as you can see, these are about absorbed moisture, how much will be there in the electrode, and so many ZmL of hydrogen, etc. All those details will come over there. Okay. So to remove this hydrogen moisture, what do we do?
Baking for electrode baking.
I don't call preheating. Preheating is a welding term. Electrode baking. Okay, so what's the baking temperature?
As per the recommendation,
Strictly as per manufacturer recommendation, you don't put your own. Because if you don't heat enough, it will not remove moisture. If you overheat, you will damage the coating. Okay. You may have seen sometimes if they are overheating, how much rebaking to do. Everything has to be by consultation with manufacturer electrode. He said 250 degree for 1 hour. You keep 250 degree for 1 hour. Now you have given it to the shop and it has come back. Now you want to bake it again. Can I bake it, or will my electrode get damaged? Okay. Now, another question I want to ask you is that if water, boils at 100 degrees centigrade, why I need to heat to 250? 300, 350, why? But it is not only free moisture, there is some moisture that has become part of the structure of the coating. That has to be removed, and that bond will not break at 100 degrees. So I have to go to 250 or 300 or 350. The only manufacturer knows what is the correct time and temperature. Both should not be exceeded. This was for the carbon steel electrodes 5.1, 70, 18, all that, and 5.5 is for this 5.5 is for the lower steel electrode. Is more or less similar, except that we have all the suffixes now that tells you the chemistry. 8018 C1. So what is C1? Read the book. It has 1% nickel, or C3 has 2% nickel, whatever it has, you have to read the book and find out. And preferably, because see, one thing, keep in mind always that when we are doing welding or making anything, we are making at the room temperature. for use at 300, 400, 500, whatever is the, if it's a pressure vessel, you can go to that temperature. Who has checked at 500 or 400? Nothing. You're just to assume that what I did will work at that temperature. So the best way to assume and make sure assumption correct is to match chemistry with chemistry. Then it is likely that there won't be a problem. Now you see, you can put off the lights wherever.
The small notebook is for you.
Thank you. Thank you.
See. Okay, doctor. I'll catch up with you.
If you put off the light, you will see the video better. The front one, yeah. Okay. Let's see if you can. You can't see. See if you can see or can't see. Yeah. Now there's a problem. Pura IT wale ko. The video is not showing it, showing me here.
TV is not very compatible.
No, it should not. That can't be the reason.
For downhand welding, particularly with heavy electrode coverings, the tip of the electrode can be dragged lightly along the joint. The arc length, in this case, is automatically determined by the depth of the cup at the tip of the electrode and the melting rate of the electrode.
You can see what vigorous reactions are
Vertical
happening.
or overhead welding, the arc length is always gauged by the welder. The proper arc length in such cases is the one that permits the welder to control the size and motion of the molten weld pool. The same is true for the root passes in groove and fillet welds.
So you saw the reactions which are intense, which are happening in the weld metal because it's a miniature steel making happening. The iron is coming from the electrode, the reaction happening with the constituents of the flux, and you are getting your weld metal, which is having your 70,000 UTS, 58,000 yield, 22% elongation. You are getting in the weld metal because of that. Okay. Now let us talk of hydrogen. Okay. Now we have to see what is this hydrogen in steel. Have you anyone seen hydrogen? I'll show you. Yeah. Like okay. So to determine or to see the effect, now this is things that I did on shop floor to show people what I'm talking. Because you talk hydrogen preheat karo, ye karo, wo karo, very easy to talk. What is it happening? So you have to take this rectangular piece in 3 pieces and it is fitted in this jig. Okay, this is your test piece. You go to the welder, pick up his electrode from his quiver, the one which he's actually using, and deposit in these three pieces which are tightly joined together, just mechanically, deposit the weld metal over that. Then immediately open this, break off these two, quench in water, remove the slag and put it in a beaker of glycerin. And this is what happens. This is your sample piece and this is your weld metal and it has been dipped in the glycerin. This is glycerin over here. And within a minute, you will see this effusion of bubbles from the surface of the weld metal. As you see, look, the bubbles will rise because it is glycerin, very viscous, they rise very slowly. Otherwise, they would have just gone up to the surface. And they will rise and rise and rise until there is a flood of hydrogen. And this is something that nobody can believe until they see it. So this experiment is done on shop floor in front of them, and it's very easy. There's nothing to do. Just take those three pieces and break it and put it over here, and you get your hydrogen in the glycerine. So then they realize what he's talking about, that this something is coming out of the weld metal. Whatever it is, call it hydrogen, call it what you like, and that's not okay. So depending upon the quality of baking, you will get more or less. This is the worst case I've taken, of course, but this is how you demonstrate these things. Next, come to GTA welding. Now here you have got a smaller slight complication where you need a proper torch, a tungsten electrode, which is supposed to be called non-consumable in the sense that it doesn't go and melt and go into the wet food. So this is a tungsten arc. Against that one was a metal arc. Metal arc was making the arc and giving the metal. Tungsten arc is giving the arc and the metal is coming separately. So you have better control over here. You can heat how much you like, you can put how much rod you like. It's easier process. It needs a gas shield of inert gas, that is typically argon over here, and a power supply to give you this, and mostly it works on, it can work on AC. Where does it work on AC? When does it work on AC? DC. AC? DC, EM because I want less heating over here. It will work on electrode positive, but it gets too hot. Sometimes you need. AC also you need. You need or no? Yes. Where?
For a thing.
No. AC for aluminium.
Yeah.
Because there's a cleaning effect from the surface of aluminium. So that is when you need the AC. So you know that AC current, what is the cycle? What is the AC cycle? What does AC look like? AC stands for alternating current, but what does it look like? Yeah, sinusoidal. So, okay, one cycle. Going from positive maximum, negative maximum, whatever is the voltage you have set, and this is your one cycle. So now you see I have got zero current, zero voltage, zero current, zero voltage, zero current. So I'm going to work on T. So the current R will go off at this point. No current, no R. Then what to do? Same with SMA. You said AC, I can do SMA. Yes or no? Yes. Or you change your mind? Yes. What happens here? 0, 0. Yeah. Then? Arc has to be restarted. It does go off. In SMA, what happens? At this point, wherever it is close enough, the arc actually goes off. But because of these materials, agents which are there in the coating, the conducting path remains. See, how do you start the arc? How do you start the arc? You scratch start and you lift it up.
So the screen is not getting shared.
Because see, I was showing a video and then the video showed all the wrong things. So I don't know what is happening here. Then I went back to this. I'm glad that the people online are awake. Next time I show the video, again it will happen when you come back. So in the SMA, ionizing agent is there in the coating that maintains the conducting path so that when the voltage rises again, the main current can flow. That is why AC electrode can be used in DC, but not vice versa. Because when I'm having a DC requirement, I will not put those agents which are going to cause ionization. I don't need. Everything costs money. So you can do AC electrode on DC, but not the reverse. Now come to tin. Now there's no nothing. No. So what to do? We have to maintain the ionization of the gap so that the current can start. When the voltage goes up, the current can start flowing again. How do we do it? Have you heard of high frequency start? In TIG, if you do scratch start, small contractors, they do that. But a piece of the tungsten electrode can get embedded in your metal. So it is better to use a high frequency. That means what to this circuit, a high frequency current is applied. The moment this comes near, not touching, near, it opens up the path. High frequency can break down the insulation of the air and a current conducting path is created, the main current starts flowing. So in AC, when I want to weld on this, that high frequency is continuously on to take care of 100 times a second, 50 cycles. It is going to go on and off. So once the high frequency is kept on, you'll hear when you go next on AC, the hum is always there. Whereas on DC, there is no sound because there is no high frequency unit. So this high frequency unit makes it good for starting, initial starting, and necessary for AC whenever we have. So in DC, we use it for the starting, then it cuts out. Automatically, the high frequency cuts out once the arc has started. So this is now the system. You can see it's got a bit more complicated than the simple SMA system because now you need an inert gas supply. All this is controlled from the power source, and you have got a cooling water supply also controlled so that moment I switch on and start welding, all the systems start working. So my cooling water supply will start cooling the torch. The gas supply will feed gas to the torch, and the high frequency, whatever are there, they will cut in. This foot pedal, as you can see, this is an old system where it was manually operated. So I first bring the torch, press the pedal, start the frequency, high frequency, and then continue with DC. Okay. Now power source. We talked of power source for SMA just briefly. I said that you said the current only. You don't said anything else, right? What was that? So basically we have voltage versus current. Okay, and this curve goes something like this. This is called a drooping characteristic. Okay, so here is the voltage and this is our working region. For example, this may be 60 or more than 60 volts, maybe 80 volts also, open circuit voltage. The working voltage is 25 to 30 volts. And as your, due to metal transfer or the man's shaking hand, my arc electrode end may move little up and down from the jaw. So the arc length is changing. So voltage is changing. So once the voltage changes from here to here, you can see that the change in current is very minimal. That's why it is called constant current. If it were not that way, I could not control the arc. Nowadays, you have machines that have this type of electronically controlled. So this is the short circuit period. It has to remove that. And initially, at the moment you start the arc, no matter how much is your variation of voltage, the current is not changing. That is the latest now electronics. Not the latest, but it came later. Similarly, in GTA, what power source would I use? ACEN. What characteristic would I use? There's a type of power supply. What is the constant voltage? What is constant voltage? What is constant voltage? This is your constant voltage curve. So if my voltage changes from here to here, is the amount of current change. Would it work? Can't allow, no. It's a manual process. I must have constant current. Same power supply will supply GTA, same power supply will give SMA. Both are working with the constant current power supply. Now you can see the process now. I don't know what will happen to those fellows. Not coming.
Vitalize. Common applications for fatigue.
This was extended. Now I put on duplicate or something.
Vitalize. Common applications for fatigue process include welding longitudinal seams in thin wall pressure pipes and tubes on continuous boring belt, usually in alloy and stainless steel without filaments. Also using film vessels in producing heavier gauge pipe tubing, chemical, petroleum and power generation industries, and also in the aircraft industry for airframes, jet engines and rocket motor cases.
show you again.
Common applications of the TIG process include welding longitudinal seams in thin wall pressure pipes and tubes on continuous forming belts, usually in alloy and stainless steel,
Nothing is
without
happening.
filler metals.
Pure melting.
Also using filler metal in producing heavier gauge pipe tubing for chemical, petroleum, and power generation industries, and also in the aircraft industry for airframes, jet engines, and rocket motor cases.
Okay. Right. So you are talking about electrode negative, electrode positive. So this is the basic understanding of that. When I have electrode negative, electrons are going from electrode to workpiece. So heat balance is 70% of heat is generated here and 30% at electrode. So less cooling effort is required because I have to remove all the heat that is being made from over. If it is positive, it is 30% at work only and 70 at here. So I have to do a lot of, and the penetration also is changing. And AC is balance. Okay. Right. So AC is what is commonly used. 50% at work and 50% electrode. Now with electronics, they have made many more modifications, and they say that only it needs to be at 10% positive and 90% can be negative. Still, the cleaning will happen adequately. So all those developments keep happening. Chemical composition requirements of tungsten electrodes. This is only for you to information that this is a spec 5.12. This section 2 part C, electrodes. So you have got EWP, that is what? Pure tungsten, then seriated tungsten, lanthanated tungsten, 1.5 lanthanated, 2% lanthanated, thoriated 1%, thoriated 2%. This is the most common one, what we are using for the carbon steel. When you go for aluminium, you go for a pure tungsten or a zirconiated tungsten, one of these. These are the ones used for this. So you have to change the electrode also with the material for the current change. And we have used the thoriated otherwise. Filler wires will be now absolutely matching the job. So 316 job, I want 316 filler. 304 job, I want 304 filler. 51670, I want what? You can't get 70 filler. It's a filler of matching chemistry, and we hope the strength will come. It's not that if I pull the filler, I'll get 70,000 PS. I know, because it's melting, no? So no meaning. The solidified material has to give the strength. So I have to match the chemistry. This is for 5.9 is for stainless steel electrodes and rods. And the first two designators are ER instead of E. And EC for composite core or standard wires and strip electrodes and things like that. 5.10 is for aluminum alloy welding rods and electrodes. 5.14 is for nickel and nickel alloy welding rods. 5.16 for titanium. 5.18 is for carbon steel for gas shielded arc welding. So this will cover TIG and MIG actually. Gas shielded arc welding. So that brings us now to MIG. Now what have we over here? We have got our MIG welding gun. What is the function of the MIG welding gun? I have got a gas nozzle which now need not be inert gas. It can be an active gas like CO2. It can be a mixture of inert and active gas, argon CO2, argon oxygen, lot of things are possible. And this wire guide and contact tube is the point from where the current is fed into the wire. You have got a gas nozzle for shielding. As told you, it is active or inert gas. And you have got over here, which you will see in next slide, the other requirements. Basically, a shielding gas has to come, and also cooling. If it is required, cooling water also has to come. This is the total schematic where I got the welding gun. Electrode feed unit is the wire feeder unit. This comes in many configurations, 2-roll, 4-roll, push-pull, lot of things are there. Planetary drives. This is a spool of wire. The advantage here now is what? That if this is a 25 kg spool of wire, I can theoretically keep on welding until the 25 kg are consumed. But when I'm doing SMA or GTA, it's a, what's the length? What's the length of the SMA rod? 450, 18 inch भी होता है. SS rods are smaller. Why? They are smaller. They may be 250 or 300. Why? There's reason for everything. I'm going to have less productivity, no? Each time I have to change my rod. Every 2 minutes, my rod finish, I have to change my rod. Yes. Then he'll call me, then I'll have BD cigarette and go and come. It is related to that thing what you read in the current. Right? So what did you say? Do not exceed 90 to 140 amperes. Why is that limitation? Here I am having a 1.6, for example. 1.6 mm pole wire. 1.6. And I'm feeding 200, 300 amperes. Right? When I put SMA, I'm saying 3 mm wire. No, 90, 100, 110. That much only. Why? Heat input where? Everything is heat only. Yeah. But where? I told you, see, I always give the answer before, but you are not listening. That's the trouble. This is where the current is going to the rod. Okay, and that may be 2 inches or whatever distance between this and that. I have to only pass current through 2 inches of welding electrode. But when I'm using a stick electrode, my clamp is here. And the welding arc is happening here. The current has to go through 18 or 16 inches of welding wire. All those hundreds of amperes. It's going to get hot. If it gets too hot, it will damage the coating. You may get a weld looking good, but it is not weld matter what you think. Therefore, I have limited current. No, I have limited the current. Knowing that this is my length, do not exceed so much so that by the time I have consumed the electrode, it will not have overheated to an extent of damaging my coating if I use that much current. So now answer my question on stainless steel. Why it is shorter?
Yeah, because stainless steel electrode need more current.
It will get hotter.
Yeah.
The same stainless steel dia wire will generate more heat. Resistivity is more. So if I have it that long, by the time I have finished half, this will be red hot. So I will damage my coating. Therefore, the stainless steel rods are shorter. And you have to strictly follow the current permitted by the manufacturer. There is no universal. So filler wires are in 5.18 for carbon steel electrodes and rods for gas shielded arc welding. 5.20 carbon steel electrodes for flux cored arc welding. What is this flux cored arc welding? Yes, yes, I know that's a short form. I asked what is it? You always give the wrong answer.
Plus inside filler wire.
Yes, it's a tubular electrode having flux inside and the metal is outside. Inverse of the SMA electrode. There are two types of tubular electrode. One is a seamless tube and the other is from strip and welded. Now you may have heard or seen problems with FCAW welding or GMA welding, porosity both आता है. Why? One of the reasons in FCA is if you have, because the wire which seam, the strip wire which is made into a round as a tube, that's having a joint. There is no RT, UT, PT, MT done on the joint. So the moment you expose it, it is going to get contaminated and pick up moisture. All these materials are hygroscopic. Once you pick up moisture, you cannot bake. Cannot bake a FCW wire, can you?
No.
So you have to weld. Even if you took out a brush fresh from a vacuum pack and you put it on the machine, immediately it has started picking up moisture. So if you keep it for 3 days and it is raining, it's going to pick up enough moisture to give you enough porosity so that this process is bad. But what is the real problem that you haven't understood? Because you are using this sasta wire, it's a cheaper wire. They will tell you, I'll give you immediate delivery. You take this wire, kuch nahi hoga, all that nonsense. But if you really want quality work in FCA, then you have to buy a seamless wire. Once it is seamless, there is no question of ingress of moisture, except the tip which is going to burn off in some rejected portion area. So you have to be careful when you think before you. So 5.20, it is low alloy steel electrodes and rods for gas heated arc welding. And welding consumable gases and gas mixtures for fusion welding. This is a very important part of the whole thing. Today our gases are actually, we are managing. Heaven is not falling. Argon deo. Okay, you are getting argon, but like I had the problem with 3 cylinders, it can happen anytime. You don't want to spend on ultra high purity argon every time because you think it's much more expensive. So to deal with the regular, this one, if you order as per this spec and you can get certified as per this spec, then you are quite sure of the quality and the moisture content, the dew point, and the amount of impurity in the gas, you can be sure. But till today, they are not, the auditors are not got into that why not ordering as per the spec of this. So this gives you the tables where he is telling you about components in nominal percentage by volume, CO2, oxygen. These are for oxidizing gases. This is for inert gases, argon, helium, what to use. And reducing gases, you can have hydrogen also mixture with the gas and nitrogen also. So this is the whole scope of the type of gases classification for fusion welding. Now let us talk of GMA modes of metal transfer. You know that GMA has different modes of metal transfer. You saw in SMA, no? Drop. That in SM it is called droplet transfer. And that's the only mode. It will go by droplet. Acha, has it occurred to you that how I can do overhead welding? If the drop has to fall down, no? Then I do overhead also or no? 5G, 6G, how do I manage? Pardon? 4G. Yeah, 4G, 5G, 6G, whatever you want. How do you do 4G? How does it happen? I'm asking. It happens. That we all know. Just asking, how does it happen? Has it occurred to you? How does it happen? And that's why that one is important. When I say all position 7018, all position electrode, it may be 28, 38, 48. Correct? Depending upon what position it is good for. Difference between 18 and 48, you don't know. You know,
One is all positions.
and 4/8 is also all position. One eight is all position and vertical up in 3G. 4/8 is vertical down also. When you do 3G, 3G welding, vertical welding, you go from down to up, no? But when you do pipeline welding, you go from top to bottom, stovepipe welding. Then can you do with the same electrode? Electrode has to be specified suitable for that particular type and technique. So if I have that 7048, I can do it. If I have 7018, I can't do it. Meaning I can do some nonsense, but it won't be good. That's what I mean to say. So the modes of metal transfer, we were talking about welding in overhead position. The metal has to be transferred. You're seeing it's happening, no?
Yeah.
So how does it happen? Because when you put that 1/8 coating you put, which is low hydrogen with all position, there are constituents in the coating that are creating gases that are pushing the drop against gravity. That's called plasma streaming. So the drop, when it is being formed, it is being formed on the electrode tip. Then these gases, they detach it and send it wherever you want. So the electrode has to be designed for that particular position. So that is a droplet transfer. The type of transfer in SMA is not changing. It is only drop, drop, drop. Whether drop up or drop down, is a drop. When I come to GMA, I have got different modes of metal transfer. And we need to know those modes because in some modes of metal transfer, doing only RT is not good enough. You have to do UT or bend test for qualification because of problem with the heat input and lack of fusion, which he says not good enough to detect by radiography. So you have to do bend test by section 9. Okay. So let's just understand the different modes of metal transfer in GMA welding. So these are globular, spray, short circuiting, and pulse transfer. We'll see the videos of each of these. Put on the right. Now these don't have sound, but you can see very interesting close high-speed photography has been done to show you exactly how the molten metal, this is the electrode, small dia electrode, and the globule, what you call the droplet, how big it is under it's partly the argon and CO2, how it breaks and detaches and goes to the weld pump. Another one will start forming, grow to big size. Ultimately, it will detach. It blow up also, so you got some spatter, and it will. Rest of it is going to come into the weld pool. It doesn't go directly. It goes all over the place and then finally lands up somewhere. Luckily, we are able to get a decent weld out at the end of it. They each have different shape, different size, and goes in a different direction. And there is reactions occurring here also. It's not just a simple melting. There's a change in the chemistry and it makes weld metal in the end of it. But less reaction than with the flux. Maybe there are more videos are there. So this is globular transfer. Next, we are going to see what is called spray transfer. The conditions under which voltage keeps changing. And here you see what is happening. The electrode is going into a sharp point from where tiny droplets are being go in a much more controlled manner. They are being forced to go in the direction where you want it to go. That is typical of spray transfer. And you get at high currents, you get a good penetration, you get everything much better. You can see it's a much more controlled process of transfer happening over here. Sometimes you saw spatter particles going. It's more or less going into a stream, you know, from the tip of the electrode, it's streaming into the well pool. Spatter will always be there. You can see it's part of the process. So you have to accept some spatter. Question of how much spatter. Then we have what is called short circuiting transfer. This is the thing where you have to be careful about your qualification. See the difference between the previous two and this difference. You can see apart from the welding condition, voltage is very low. That time it was 35, now it's only 20. So you get a very short arc length. And you can see as the droplet is forming, it is so close that it goes and touches the weld pool and there's a short circuit. Then as like a fuse blows, the short circuit is clearing itself with some spatter and you get another droplet. Now this is happening 150 times a second. These are very high speed. So ultra slow motion pictures have been taken, but this is happening so fast you couldn't see it otherwise. And this, because there is no arc here, the heat input is less. Because heat input is less, there is possibility of lack of fusion. So when he says qualifying by short circuiting, you must qualify by bend test only, not by RT. RT will not show you if it's there, the lack of fusion. And see so the whole this thing, dynamics of this depends on the ability of the power source to control the short circuit current. If it doesn't control well, there will be spatter. If it controls well, then there will be less spatter. But spatter will be there, some amount.
So this video is for 1G position, right?
Yeah, sure, yeah.
So you have 4G position.
They haven't shown it in that way because they were concentrating on the metal being transferred, how it is being transferred. not the position. It is not specified. You are just assuming because it is appearing 1G that it must be 1G. I also assume, but it is not specified that way. So this is what we are actually this is the arcing period, and this is the short circuiting period where the current is rising. Then it blows up the fuse, and the current was rising, then current begins to fall. Then there's an arcing period, again short circuiting period. See extinction. So the arc has gone off. Now the fuse has to blow. So slowly the current and this is increasing until it blows. Then it goes back to the working current like that. So this is short circuiting voltage oscillogram. Then we have the pulse spray transfer, which has got some sound, I think, so you can understand.
Pulse spray transfer sprays a stream of tiny molten droplets across the arc from the electrode to the base metal. But unlike spray transfer, the stream is not continuous. The power source rapidly pulses the welding output between high peak currents that cause the transfer to spray and a lower background current that maintains the arc but does not allow any metal transfer to occur. The pulsing of the current produces a buzzing sound.
So you saw small drop formed, a high current pulse came, pushed the drop out. So it's controlled, very much controlled in that. And it's a very good balance because the low current, background current allows you to weld on with less heat input. And just one pulse comes to push the droplet into the pool, and it's very well controlled. Okay. Okay, so that ends that. End of the movie show. And only 2 slides, then we can have chai. So submerged arc welding is the other process that we are talking about. This is about high current and high, can put on the light, high current and high deposition. You want to fill up 200 mm of that, you can't do it with GTA, it'll never finish. So we go in for SAW, sorry. So this is basically, we are having a layer of granulated flux. This is the electrode. An arc is generated under the layer of flux. The flux melts, makes the weld metal, makes the solidification oxide on top, makes the weld metal, and this moves forward. It is continuously fed from a hopper, and the balance unused flux is sucked back into the hopper and recirculated. Whatever is melted, gone, goes as the slag layer on top and protects the welding. So you get very high current because now I am talking there, we are talking 1.6 mm, here you're talking of 4 and 5 mm electrodes, currents of 600, 800,000 amperes. You can imagine how much of this one we are there. AC, DC, both are applicable. And this is the schematic of the flux feed tube. It is feeding in front of the electrode and arc. Then it melts, and from here you pick up there. So you have solid slag. This flux helps only to prevent it from spilling and being wasted. Otherwise, you have got the same current, you have got the same contact tube here, which is the ones feeding the wire. The current is fed at the tip, not a mile away, not at the end of the spool. Otherwise, you couldn't do anything. Otherwise, it's all AC, DC, and you can work on positive, negative, everything. And these are the typical You can see the single layer, how heavy it can be. For classification, now again, we need to have the adequacy. Am I using the right strength consumable? We talk about chemistry, they are all interrelated. So if I want to classify welding consumables of SAW, I must classify flux wire combination. So the flux wire combination is designated as F for the flux. Then this one gives you the minimum tensile strength in 10,000 psi. So F7 means 70,000 psi, whereas there E70 into 1000. Here 7 into 10,000. Okay, F7. Then next one designates the condition of heat treatment in which it is good. So A is as welded, P is post-weld heat treated. So you have to make sure that if your job is getting post-weld heat treated, you get a P. People have made all these mistakes, don't worry. They get an A, then it fails in the heat treatment, and then they ask me, why did it fail? You got the wrong electrode. So when the manufacturer is giving you an option of A and P, you have to buy the right thing. So FP, and then this 2, 3, 4, 5, whatever is the indication of temperature at which the impact will be acceptable 27 Joule. So F7A2 means it's good for minus 20 F at 27. The all American, no, everything F, they understand that only. So you have to convert into your history. The 1 or 2 digits indicate the temperature in degree F at or above which the impact strength meets 20 foot pound in 27. And then these are next important is now the flux with this electrode. This will give you the chemistry. So EH14, for example. I go to my table, EH14 is listed there. This is the carbon, this is the manganese, this is the phosphorus. I match my chemistry and the strength, and I then use it. Okay, rest are optional supplement with designated and whatever. Okay. Okay. Now we can have chai, then we can have all your questions.
Laser welding is type of process
Light. So the light is concentrated into a very narrow beam. Very temperature. You can pierce directly. And then you move along the schedule. There's plasma welding, there's laser welding, but these are not common shop floor processes. You have to go to a particular place to get it done. Thank you.
Hold